So I wanted to talk a little bit about trying to live stream a balloon launch. And so we'll talk about what our objectives were for a flight. We did one about a little over a year ago. So the objective was to send some live video from the payload to the ground and to transmit that onto YouTube so that we would have, we could get some excitement from people who weren't on the balloon chase, seeing what was going on in the balloon in real time. And at the same time, what we wanted to do is take that video along with any video that we might have from people using their smartphones to record what's going on, to do a live video feed and basically curate it and have basically a producer in a station put together basically our broadcast. And so we had a producer type person curating a broadcast. And so we tried this and we were very novice at it, and the result was kind of lumpy, but we did get it to work. So here's an overview of what we did, and let me get find my tools here, annotate tool. I guess everybody's using the little laser dot if I can find it. Here we go. You seeing my laser dot? Is my laser dot on the screen? Okay.
Yes, sir. Yes, sir.
All right.
Yes.
So let's move something over here first. Okay, so yeah, the idea was here's our producer who's sitting at a computer at Cornell, and he's going to take all these streams coming in from either mobile webcams or receive stations that are receiving video and sending them out, and then put together a broadcast on YouTube. So it turned out that because this broadcast station was sitting on Cornell IP space and 10 space IP space, and these mobile phones are also sitting on 10 space networks on privately routed networks, we had to put something in a publicly routable space. So we put an RTMP server, for those who are familiar with it. And it's basically a streaming server that takes streaming video in and lets you yank it back out. And so this server, the RTMP server, was on a public network on campus, and that way devices with private IP addresses could send data to it, and this producer who was on a private IP address could suck data out of it to send off to YouTube. So that was sort of how we had to deal with the network addressing situation. Our receive stations, I show two of them here. We had basically mobile receive stations that had, we used 1.2 gigahertz FPV camera and or FPV transmitters and receivers, and we hooked them to a device called a Dazzle, which then presents a USB camera into our computer, and then we take that USB camera, and over a mobile IP tether, we send it through software up to the RTMP server. So we had a couple of these mobile stations receiving live video, sending them to the producer, as well as anything that our students who had their phones might want to send along to the producer. So some software choices we made. We used a software called XSplit Broadcaster. There's a free version available, and you can buy inexpensive short-term licenses. You can buy it by the month for 3 months, whatever, which is kind of nice for our application. So we chose to use that. It can take multiple input sources like cameras, windows on your computer, RTMP streams, and then publish them out to YouTube. So our producer was running XSplit Broadcaster on his computer, and in fact, we ran XSplit Broadcaster in our remote receive stations as well. And as I mentioned before, we ran an RTMP server on campus, which, and I can't remember what RTMP stands for, something protocol, to solve our NAT and IP addressing issues. And that's probably a little bit too involved to discuss here, but it solved addressing issues by allowing us to have a public IP address on the server that we had to send data to. So that's why we stood up one of those on a Linux server. So the video capture showing here is what the video receiver looks like for a 1.2 gigahertz basically FPV camera. Basically it has video out, and you plug the cable into video in on the Dazzle, and out the other end of the Dazzle is a USB camera presented. So that was a very simple off-the-shelf solution to receive the video and put it into the computer, which then we just pumped into XSplit. 720p resolution was just fine because that's all the FPV gear could really handle anyway. And the dazzles are actually quite cheap. I mean, even new, they're only like 70 bucks, but I was able to find several of them on eBay. I bought a couple just to have multiples for the receive station, and they were like $14 a piece used. So that worked out really well. So let's talk a little bit about transmit and receive testing. I had to calculate basically how much power we needed to transmit with to actually receive video from space, and antenna testing and power consumption and so forth. So again, like any good geek, when I want to figure something out, I Google, and I found a free space path loss calculator, I think by putting the words free space path loss calculator in Google. And I was able to plug into it 1.2 gigahertz and assume 30 kilometers at apogee, which of course isn't the greatest distance we're going to be, right? If it's at apogee, but I'm 60 miles down range, you have to sort of do the hypotenuse of the triangle kind of thing. But, you know, for benchmark purposes, let's say 30 kilometers, hit calculate, and it basically came up with a number of 123 dB. We know that S9 reception, solid reception for audio is good at about 73 dB. So I thought 73 dB would be a reasonable thing to kind of gun toward, or at least to know that I was in the ballpark for receiving decent video. So in this calculation, I assumed no transmitter receiver gain. I just wanted to know where I was starting from and how far I had to get. And so it's showing 123 dB or minus 123 dB. I wanted to get to minus 73 dB, so I was 50 dB off. So I needed to make up some ground there. And yeah, there's cable loss and everything is kind of ballparky, but that's sort of, you know, what I was looking at. I wanted 50 more dB. Well, it's pretty easy to get to 50 dB when you start out by using a 2-watt transmitter. So I got 33 dB right there. And so taking that from 50, I needed about 17 dB more gain. So helical antennas, it's been sort of a theme in my life this year. So 3-turn helicals in the calculator that we showed you in the previous presentation claim to give you about 19.5 dBi gain. So you think, geez, if I put a helical on the transmitter and the receiver, I've got another 19 dB of gain right there. And bingo, I'm up, you know, I'm about where I need to be. Well, it didn't work out that way, but we got closer. So antenna selection and testing. Again, I wanted to go off the shelf as much as I could. So in this case, I used anybody who does FPV stuff know IB Crazy Antennas. I think he now calls himself Video Aerial Systems, VAS. But everybody remembers the guy, his handle online is IB Crazy. Makes a 3-turn 1.2 gigahertz antenna, which is here and looks suspiciously like the cheesy one that I 3D designed later. And he rates it at 7.5 dBi, which I thought was interesting given the calculators say 9 dBi, but okay, let's be conservative and say 7.5. And I actually made some knockoff clones of this antenna using a piece of sheet steel, a 3-inch mailer tube that I cut to length, and just wrapping a wire 3 turns around it. And we actually made some pretty competent, cheap knockoff antennas that way. And here is the gain pattern. And again, it's going to have a 60-degree beam width and have decent gain there. So we decided that on the receive station, since we can sort of aim toward the balloon, we would get 7 dB gain, 7.5 dB gain by using these on the ground. The transmitter solution was a little more difficult. Our experience has been in payloads that they flail around like crazy in the sky. And if we tried to use something too directional, that we would get ourselves into trouble. So we decided to give up on the gain there and go with a 3-turn omnidirectional cloverleaf antenna. So this cloverleaf, if you look at the gain pattern, it is just round. It's very nice. And in fact, out the top, the gain is pretty good too, or pretty flat. It doesn't lose much, even if you're we mounted this antenna upside down, actually directly under would be here. This is skyward that way when we installed it. Gain was just uniform everywhere. So we decided to do with that. They said, negligible 1 to 2 dBi of gain. So we chose omnidirectional so that the payload could flop around wherever it wanted and we would still be getting decent signal. So we did some real science here. We set up a transmit and receive station. So we set up, this is the transmitter here, and we just used a cheesy dipole antenna they provided. And we set a receive station over here with a cheesy dipole, and we just pumped it into a spectrum analyzer to benchmark how much signal we were receiving. And then we fooled around with antennas on both ends and compared the results. Basically the net result was we were getting about 10 dB of gain when we hoped for 19, but yeah, that's okay. And the directionality was actually quite good with the choice of antennas. If we pointed the three turn helical in the direction of the cloverleaf antenna, we could turn that cloverleaf just about any which way we wanted, and it really didn't impact the signal strength that much. So we felt pretty confident that if we were aiming the antenna properly and we were getting any signal at all, that we didn't matter what the payload orientation was doing too much. So the next thing I had to do is figure out, okay, I've got this 2-watt transmitter, it's going to be drawing some current. How much power are we going to have to send? How many tons of batteries do I need? During testing, typo there, we were using a 4S5500 LiPo. And it turns out, doing some looking at the current draw while it was running, we were using maybe 600 milliamps of draw when everything was running. And since we had a 5500 milliamp hour battery, we were doing really well. So it ran over 6 hours, and I just stopped well before the battery died. That said, I kind of chickened out when flight time came, since I knew that I had good measurements and good tests, and knew that we weren't going to draw that much current. I went to my old standby AA ultimate lithium batteries. I wired 8 of those in series, which gives us between 12 and 14.4 volts, and 3,000 milliamp hours. And I just trusted that those would last me more than 3 hours, and that's sort of my benchmark for a flight. Turn it on before we launch, have 2.5 hours in the air, and a little extra time either way to make up for it. So I didn't do a full test to failure because the ultimate lithiums are expensive, but I've used them over and over again and always had good results, and have done tests to failure in the past. So we just went with it. So I built out the payload. So I'll talk to you a little bit about all these things here. So the camera, GPS, and on-screen display. So basically we had a camera and I had an on-screen display module, and that thing's about the size of a quarter. And we pumped the camera into it, and I hooked up a GPS module and pumped the GPS into it. And that allows us to overlay GPS information onto what the camera is seeing, pump that into the FPV transmitter and into that antenna that we had. And that is basically what our live stream payload box would do. Also, the on-screen display could overlay our call sign to comply with FCC regs, and some additional data because we're geeks, so why not? So again, the antenna and transmitter were pretty straightforward. This is just a standard 1.2 gigahertz transmitter you can buy on Amazon or whatever. And the video, we feed in the video coming out of the on-screen display module into the video in, and there's the SMA antenna and the SMA connector, and just out to the antenna. And again, we mounted this upside down, and I'll show you an illustration of that in a moment. So this is an example of what the on-screen display looked like. We had put our website there so people could search our club to see what the heck this is if they happen to be out flying their model airplanes on 1.2 gigahertz, and all of a sudden they saw, well, none of their planes were in the air. They saw space and wanted to know what the heck was going on. They could follow this URL. And we put the latitude, longitude, the current altitude. Here we're at 30 kilometers, the value of the battery. And it turned out this was horribly calibrated. I did not notice that when we were testing, and needed to correct that, but the batteries held up just fine. It was flashing our call sign down here on occasion. These numbers, current speed, kilometers per hour, was 82 kilometers per hour. So it was traveling over, as the crow flies, 82 kilometers per hour. This was peak speed. So peak speed was 144 kilometers per hour during the flight to this point. Likewise, the current distance from the launch point was 79 kilometers, and the peak distance from launch point was 79 kilometers because this flight just kind of went straight. It never turned back on itself. So that's the data that we overlaid on the camera view. And this is actual camera view from that flight. And you can see down here the long finger-like lakes that we have in our area. So here is a discussion of the power system. So we had our AA Ultimate lithiums, pump those into a 7805 regulator to drive the GPS and the on-screen display module, as well as a Foxier camera, FPV camera. And all that total is maybe, you know, they're each rated at like a 100 milliamp, but they don't draw anything near that. And then I found that this FPV transmitter, when it was transmitting, was drawing about a half an amp. All put together, it was actually drawing about 0.6 amps, 600 milliamps. So here's a little board I whacked together. So we were taking, I believe this cable ran off to the batteries and pumped that power right back out. This is the cable, this cable here on the FPV transmitter. Put a socket on the board for that. The on-screen display module, which runs off 5 volts, sends it off to the GPS. So this cable runs to our GPS and is fed 5 volts. And this cable leads to the FPV camera, which runs 5 volts. And I put all these special connectors right on this board so I didn't have to do a whole lot of surgery on my devices, just use the cables they came with. Nice thing about having a deep parts bin. So that was a little custom board I built for the power and routing of the video. So here's how it came together inside our payload box. You see the power board I just showed you, the block of Energizer Ultimate lithiums, and basically just plug that into that connector and it's powered up. Here's the video transmitter. You can see the SMA connector coming out and basically going straight downward from where we're viewing. We're viewing from the top. Straight down is the antenna. So the antenna is underneath this foil. I wanted to keep some RF insulation between the antenna and the GPS module because we've had trouble with that in the past. So I put a foil layer here. The FPV camera is right here. So the camera goes right into the board there. So that's the top view of the payload box. A little more detailed view, you see the transmitter, and I, with very sophisticated mounting hardware, that being strapping tape and zip ties, attached it to a gigantic block of heat sink just because this thing does throw off some heat. And I wanted to make sure that we kept it cool. So the heat sink is still inside this foam box, but it was just to distribute the heat a little bit. And in flight, we didn't really have any problems. So I think that all worked out just fine. And again, here's a 90-degree angle, and it just goes down. Here's the connector on the cloverleaf antenna going through a hole in the foil and through the floor of this, this platform here. This is the GPS, or this is the top of the lid put back on the box. And I had the GPS module on the top under some clear tape. And just again, for a little extra protection, I have a ferrite in there and I wrap these wires around a ferrite, again, just in case some of the RF from that video was getting up here and trying to annoy the GPS. And with all those precautions, the GPS had absolutely no trouble, even though there was 2 watts of video spraying out beneath it. And we've had trouble with GPS modules in the past with strong RF nearby. So here I overlaid onto this picture, a picture of the camera. So you saw that the transmitter module was in here, had a 90 degrees. And so underneath that platform, which is about here, is where the antenna sat inside the box. And so there it was nestled nicely inside the foam. There was a foil between it and the rest of the payload. So RF had more trouble getting upwards, and this was aimed downward. And that way the antenna was nicely protected inside the payload box and held up just great. And here's the FPV camera that's just aimed out at a 90-degree angle. So for receiving in flight, this is the top of my car, and I literally mounted the 3-turn helical on the roof and ran it down to the computer gear that I have inside the chase vehicle. So this is what we were using to receive at launch time and for the initial portion of the chase. So this is a view of what our producer was putting up on the web based on all the stuff that was being fed into that RTMP server. So he had live video coming. This is from the chase vehicle, sending it over my cell phone tether. So we had the payload camera here, and this is when we were just at 1,000 feet altitude. So we weren't very high at all because ground level there was like 700 feet or something. And then he threw a couple of APRS maps up here, a prediction map, and I don't know what else he had. Our producer is actually an AV guy. He knows nothing about weather balloons and tracking. So he was kind of at sea when it came to putting other stuff here. And he also really wasn't very familiar with the software, so he was learning it as he went. But, you know, we threw a little banner down here and date and time. And so that was what we were live streaming. And so that we could share that URL with people and they could see what we were doing. So here is our launch, and you can see this is the actual data from the flight. You can see it was pretty linear. The problem we had is that our launch site was over here. You see I-86 is over here, and I really wanted to take the interstate because the goat trails through here are kind of slow. So I had to take the interstate, which actually went like this to get back up here. And it turned out that when the payload was low in the sky, that was just far enough south that basically I got outside of that sort of 60-degree beam width I had looking up. So pretty much the minute I went down Route 14 here, we lost the payload from the chase vehicle. But what was impressive is that my friend Kent was over here in Newark Valley. He was on a hill on this side of the valley with an antenna looking over, and he started receiving the payload about here. From the ground all the way over here at about 60 miles of range. So he was able to transmit most of the flight from that location. So here's his first reception. We were at, this is altitude in meters, 7,000 meters. So we're at 7,000 meters. Again, you can see the Finger Lakes there. Whoopsie. You can see the Finger Lakes here. And at that point, it was 56 miles away from where he was. And this is sort of the first of the picture he got. The picture only got better for the rest of the flight as he received it from his station. And he had a great time talking to all the people who pulled over to ask him why he had this ray gun pointed off to the west. And he would put the FPV goggles on them so they could see what was going on. And they would have to grab onto his car because they would try to almost fall over as the payload was swinging. So we captured the balloon burst, and this is where we're going to share out the URL. Mark, do you have that URL to share in the chat? I don't have the chat window under.
I don't think I have it handy. Let me see.
Oh, let me see if I can find the chat window. Where's my chat window? Give me a chat window. Ah, I closed the chat window. Now I can't find it.
Yeah, let me see. Did you email it to me?
It's actually in the schedule.
Oh, here it is. Yep.
You got it?
Got
okay.
it. Yeah.
Great. So you can put that in the chat. This is only about a 40-second video, so I'll give people a minute to bring it up if they want to watch it from home instead of through the interface here. Basically, this was apogee. So here's the story. I showed you on that previous foil that the data has to go through a lot of hops along the way. So when Kent was in Newark Valley receiving this video, he's receiving it in real time. While we were chasing to facilitate communications, we set up a conference call. So I had my cell phone in the truck and I'm screaming down Route 86 at 70 miles an hour. And I'm in conference with Kent, who's at the receive station 60 miles away, and also with Matt, who is our producer, who is at Cornell, who is 40 miles away. And so when Kent receives the video, he's the first one to see it. And then he streams it through his cell phone tether to that RTMP server at Cornell, which then goes into the production station that Matt is seeing. There's about a 10-second to 15-second delay between when Kent sees what he sees and when Matt sees the same thing. Well, we're on the conference call, and then when Matt streams that from his streaming station into YouTube, YouTube takes about another 10 to 15 seconds to digest that streaming data and present it on YouTube. So we're in a chase vehicle, and the only view we have since I've lost live stream on the interstate is through YouTube. So we literally have on my laptop on a stand in the truck, YouTube, and we're watching the video. And what we hear as the balloon bursts is Kent say, "Oh my God, that's so cool." And we're looking and we're just seeing the balloon at 30,000 kilometers or meters. And then about 15 seconds later, Matt's like, "Oh my God, that's so cool!" At this point, I'm in my van, or screaming down the highway, and I'm like totally distracted driving, looking at the display. I've got 3 students in the car, and they're all eyes riveted on the display. And then we finally see the balloon burst. So if you want to go ahead and hit play on the balloon burst, if you haven't already, hopefully it will play for me, and you'll probably see a horrible version of it here. So as we're going, the balloon burst, and just, you can see the Finger Lakes under there. And when the balloon burst, you saw bits of balloon fly by the screen. It was just awesome. And we had this 30 seconds of, "Oh my God, that's so cool," from one person to the next. And we finally got to see it. So so that was our chase story for the balloon burst. So now I have to figure out how to tell YouTube to stop that and go to my next. No, don't show that again. Okay, next foil. So the descent. So it followed. This is the prediction in yellow versus the actual data in red that we gathered, and you could see we followed that prediction beautifully. We just descended a little faster than predicted. So Kent was over here on the other side of Newark Valley, and we landed actually on top of like a plateau on the other side of the valley. Which made our recovery take a little bit longer because it was actually pretty high up, and the trackers that I use are just 10 milliwatt, so we couldn't hear the trackers basically where it had landed. So we pretty much had to go under the last packet we saw, and then drive around and go up into a farm until we found it. But it followed the predictions beautifully. And Kent, as I said, had video all the way down to about, I think he had it down to about 800 meters, if I recall. And so finally, we did find it up on a plateau, hanging in a tree, and there's our payload box. And this was another payload that we had. We actually had 3 payloads here, and there's another Raspberry Pi in a separate box here. So we got all our payloads back. So that was the flight. So lessons we learned: the cell phone tethers were kind of sketchy for live video. You know, we're sending live video over an IP tether on a phone. So one thought might be to put receive stations in parking lots next to fast food joints that have free Wi-Fi. So for like outside of McDonald's, and we can get their Wi-Fi, they might have a faster uplink than a phone would. More receive stations are good. Again, I expected to receive throughout the flight in my truck, but based on the location, by the time I got far enough north again to be under the balloon, I only got bits and wisps of it from the truck receive station based on the way the antenna was aimed. We needed more practice. Our producer in the studio was learning as he went, and we hadn't really had much of an opportunity to play with things, and he didn't know much about APRS or anything. So, you know, the presentation that we made was not awesome, but you know, it was fun to play. And the last was we didn't really have a host. All of our people in our club are introverts, and nobody really wanted to be the talking head in the camera. So we had trouble finding a student who wanted to stand in front of the camera and just narrate what was going on at the time. And we have some inroads with the atmospheric sciences department, and there are some meteorology students who actually want to be on-air personalities. So I've been talking to a professor there to see if we can maybe sucker some of them to come and play with the ham club and actually practice being on air as part of a ham club flight. So with that, are there any questions?
Mike, that's pretty impressive distance for it to 1200 megahertz band, and that's pretty much an FM modulation too. So your threshold is higher than what it'd be if you had AM modulation TV. So very, very nice. My question was, did you measure the frequency of the transmitter? Because some of those FPV transmitters, they say they're on the 1200 megahertz band, but sometimes they're down around 1150 or 1180, or you know, they're
no, it was pretty much dead nuts on.
Okay.
Yeah, they're pretty good. Mike, have you ever used one of these?
RunCam, yeah.
Okay,
the Fox here is similar to the RunCam. It's just
this is the Swift 2, and it has an OSD built into it, and
yeah.
it comes with a little programming thing that you can go back and forth and choose all your stuff. but the RunCam Swift 2, it's got an OSD built into it.
Yeah, the Foxeer has a run as a OSD as well, so I could have done call sign and battery voltage with the Foxeer, but we also wanted to get the GPS coordinates and all that. And
Well, this does the same thing. It takes it in on my drone from the GPS. It is a GPS.
oh, it does. Okay, so that so that would have been a simpler way to do the OSD. But as it happened, I had like I got when they clearing out those OSD modules, they were like $3 a piece, and I grabbed 5 of them just to have them in my toy box.
These cameras weren't pretty cheap, but I don't know what they are now because these are about 4 years old.
So
you have to watch some of those cameras because some of them are IR blocked and some of them aren't.
Yeah, we have a lot of experience with those cameras because they're actually what I fly in my my airplanes. So I was very comfortable using that camera.
Yeah, they're good cameras.
To come back to Bill's question about frequency, I did both the transmitter and the receiver. They're not a matched pair. So like one has 8 frequencies on it, and the other has 12. But there's overlap of those 8, and so they at least have to be on frequency enough to talk to each other. And when I put it in the spectrum analyzer, it was dead nuts on with my spectrum analyzer on.
A while back, they split frequencies, and the old ones had the 8 channel, and then the newer ones had more, and then they came out with some newer ones, and they I think they reduced the deviation and they split the channels and made them closer. So they came up with more channels to have more spectrum width.
Yeah.
Yeah, I had an older one and the frequency was quite a bit off. It wasn't in the 1200 megahertz band. But that was a fairly old one. That was like 5 or 6 years ago.
There's definitely a company called Ready Made RC that makes the receivers, and they're the same receiver that you can buy from any of the people. It's the same knockoff receiver. And you see Ready Made RC just put a different sticker on it. However, if you open it up, you see that Ready Made RC has done some hand mods to put some filtering in it. They put blocking caps and filtering caps all around inside. And the Ready Made RC claims to be a much better receiver, and I would believe it. I've been tempted to take apart one of the Ready Made RCs and actually measure the values of the components because I've got several of the cheap receivers, and just surface mount solder, hack those into the other receivers I've got just to make sure that there's.
I'm sure you're familiar with Hobby King.
Oh yeah.
Yeah. They got a lot of good stuff on their website. I don't know about now, but the thing is, if you don't use the Seattle warehouse and yours is the first stuff to go into the container, you're not going to get it for a couple months. If it's the last stuff into the container over in China, you'll get it pretty quick.
All right, so if there aren't any other questions, I'm going to throw it back to Mark because we're going to have our sort of wrap up here and discussion of future GPSLs.
Just a quick comment, Mike.
Yep.
That cloverleaf antenna is what we used on our first flights 30 years ago, and they work great because they give you a nice hemispherical pattern down to the ground, and if you're right below it, it's actually kind of a circular polarization. You only lose about 3 dB if you're directly below it. So we've used that cloverleaf antenna, and so they've been used quite a bit.
Yeah, in fact, I have an ATV transmitter, and I'd intended to send to launch one of those at one point with a cloverleaf antenna. So that's why I sort of wanted to go with the clover antenna.
Have you seen the far view antennas? These are for 5.8 gigahertz, but he's got a neat little package, and they're real cheap. He sends you a jig to build them. They're a 3-layer.
Mm-hmm.
And those are the far view antennas, but they're for 5.8. I don't know whether anybody's built any for like 1.2 or anything like that.
To the EOSS group, is 36OAL still building his cloverleaf antennas, and he made some in the 1200 band too. Do you know if he's still making those? Marty, anybody in EOSS, do you know? John?
I built, you're talking about the 1.2 gigahertz, like a mini wheel?
The mini wheels, old antenna lab.
I've got one for 2.8 gig, and it worked fine up until about 20,000 feet. The ground station wasn't very good, and but it did help on recovery because as I went underneath a tree, I got the video back, and it was looking down at my Jeep. The payloads are up in the tree.
But Kent Britton WA5 VJB, I think it is. He makes the cloverleaf antennas on a flat PC board, and I've actually used them on the 900 band, and they work pretty well.
Yep.
You just put an SMA connector on them, and you're done. It's actually printed on a PC board.
Guys, one group I receive stuff from like quadcopters is Get FPV, which is firstpersonview.com. They've got stuff like that for quadcopters, and also Amazon's got a couple of books on the what were the receivers we talked about earlier, RTL receivers or whatever, and it gives you directions for making those, as well as a lot of websites you can go to buy that kind of equipment, right-hand circular polarized versus left-hand circular polarized. So I think it's RTL something on Amazon, but if you Amazon it, it'll probably pop up.
Say, Bill, am I on? Yeah. I just saw OAL at a Hamfest about a month ago, and he's playing the consulting role and isn't really pursuing building the antennas. But if you contact him, I'm sure he's got one on the shelf just for you.